Hello everyone, I'm Hyeseong Kim. I'm pleased to present our work titled TWINGS, Thin Plate Splines Warp-Aligned Initialization for Sparse-view Gaussian Splatting. Recently, 3D Gaussian Splatting has shown impressive reconstruction quality and real-time rendering. However, in sparse-view scenarios, 3D GS becomes highly sensitive to initialization. Standard 3D GS relies on cold point clouds obtained from structure from motion. However, when only a few views are available, COMET often fails to reconstruct enough reliable points. As a result, Gaussian optimization becomes unstable, often leading 3D GS to overfit to the training views. To address this, we propose TWINGS. Our key finding is that our method produces balanced foreground and background coverage, which is crucial for stable Gaussian optimization in sparse-view scenarios. Our method consists of three main components. First, we construct multi-view correspondences across the sparse input views. Using these correspondences and non-camera parameters, we triangulate reliable 3D control points in a world coordinate system. Second, we estimate monocular depths for each image and backproject the depth map into 3D space. This gives us dense points, but they are geometrically misaligned due to the scale ambiguity of monocular depths. Then TPS performs smooth non-rigid deformation to align the back-projected depth points with the triangulated control points, producing calibrated back-projected points. Our method then samples calibrated points around reliable control points to initialize 3D GS. TWINGS achieves strong performance across three benchmark datasets, especially in extremely sparse view settings. These results show that accurate initialization is critical for stabilizing Gaussian optimization and improving reconstruction quality in sparse-view 3D GS. Our method also serves as a plug-and-play initialization module that can be integrated into other 3D GS methods without changing their core optimization pipeline. Replacing COMET initialization with TWINGS init improves performance across different baselines. This confirms that our initialization is broadly applicable to sparse-view 3D GS methods. Competing methods often blur or misalign the lettering, fail to reconstruct the window framing, or miss small details such as black pupils. In contrast, TWINGS preserved these structures with sharper geometry and more faithful appearance. This shows that better geometric initialization directly improved the final reconstruction quality in sparse-view 3D GS. Previous methods struggled to preserve fine structures under sparse supervision. They often miss small details such as the ceiling sprinkler and the fine dot patterns on the marble surface. They also produce distorted object geometry over smooth regions like grass, or fail to preserve the spherical shape of the wall. In contrast, TWINGS preserve high-frequency details and reconstructs object shapes more accurately. This shows that our geometrically accurate initialization helps 3D GS avoid over-smoothing and maintain fine local structures in sparse-view scenarios. We analyzed why TWINGS init improves sparse-view 3D GS. First, the point cloud visualization shows the impact of our initialization module. The COMET point cloud is extremely sparse in the 3-view setting, providing insufficient constraints for Gaussian optimization. In contrast, TWINGS init produces a much denser point cloud while preserving the overall scene structure, with only 12.45 seconds for DTU 3-view and 17.74 seconds for LLF 3-view. We also evaluate the deformation method because aligning back-projected monocular depths to triangulated geometry is the core step of TWINGS init. Compared with linear scaling and freeform deformation, TPS produces more faithful geometry through smooth non-rigid alignment. Overall, these results show that our design choices enable dense and geometrically accurate initialization and minimal cost, leading to stable 3D GS optimization in sparse-view scenarios. In conclusion, our method provides a TPS-based warp-aligned initialization framework for sparse-view 3D Gaussian splatting. Overall, our method provides a practical and highly efficient plug-and-play module for robust sparse-view 3D GS. Thank you for listening. Our code is publicly available at the link in the description below.